Hello, welcome to today's YouTube video on application of Newton's laws of motion. So before we continue, let me specify the procedure we usually use in solving a particular problem. The first thing is to identify the body to whose motion of the problem refers. The body can be a moving mass, it can be a swimming person, it can be somebody in a jumping up, doing one form of motion or another. So the next thing you do is to identify and locate objects in the environment of the body. For instance, is it climbing an incline? Is it attached to a spring or a cord? Is it under the influence of the earth, and so forth and so on? The next thing we do is to select a suitable inertial reference frame. And axis, it can be positive, that is pointing downwards. A positive x-axis can be pointing to the left, in order to suit a particular problem that you are trying to solve, and not to make it very ambiguous. Then the next thing is to isolate the object and make a separate body diagram showing all the forces. Having identified all the forces that you are involved in the body, you make a separate body diagram. Then finally, you apply Newton's law. Newton's second law. If there is no motion, if the body is not accelerating, all the forces now will be equal to zero, and that is Newton's first law. But basically, we are applying Newton's second law. So with this, let us solve this particular problem. We have two masses of equal weight or equal mass, 3 kg, 3 kg, and the tension in the string is 0.7 m1 g. So 0.7 times 3 times g. Let's take our g to be equal to 10 meters per second squared. So that is what it will be. So first of all, now we'll identify these two bodies. These are the two bodies. The first one. So there is a string attached to it, inextensible string. So we make it, and there is a friction force. If this thing is to roll to the right, there is a friction force that will try to oppose the motion of this. This one is not resting, it's not touching on this place, so it's free to move. But this one will be acted upon by a frictional force that will tend to oppose this forward movement, if you like. Then the next thing now is to make a free body diagram. Let us make the free body diagram. So from here, you find out that there is a force Fx going to the left, a reaction force pointing upwards, and the weight pointing downwards. So let us put them. So it will be, the free body diagram for M2 will be, let's use this as M2 now. To the right is tension, to the left is frictional force, downwards is the mass times the acceleration due to gravity, that's the weight, and the upward reaction on this smooth plane is R. For this one, the free body diagram, there's no motion sideways, so the free body diagram is one that is acting downward and one that is acting upward. So the free body diagram for that one is, remember here is M2, this is M1. So a downward force, which is the weight, M1G, and the tension and the strength, they are the same because it is connected through a frictionless pulley. So T is the same. So from where this one stops is where this one gets it. This one is horizontal, while this one is vertical. See, the force is translated to vertical force here. So for convenience, that's just what we we say by selecting a suitable inertial reference frame. For convenience, remember, we said select a suitable inertial reference frame to simplify the next step. So let us choose that whenever it is going this way, you have a positive x-axis. Whenever it is coming down, you have a positive y-axis. So that means anything to the left is negative x and anything upward is negative y. So with that in mind, now we set out to solve the problem. So let us start with M2 mass 2 M2. So for mass M2, let us do first of all along x-axis, along this axis straight. So you see that along x-axis, the total force, we are now going to apply Newton's law along x-axis, and it is equal to, that's Newton's second law. All the forces will be equal to ma in the acceleration component of x component of acceleration. So we have that. So the forces that are acting along the horizontal is T and Fx, and T is in the positive direction while Fx is in the negative direction. So we have it to be T minus Fs is equal to Max. Is equal to Max. So we now see that from here that Fs is equal to T minus Max. T minus Max. Let's call this equation 1. Okay, along y-axis, that's vertical for this M2. Remember, this is M2. Let me just put the 2 here. Along y-axis, you see that sigma Fy should be equal to MAY. But the motion is along the x-axis. It's not bumping up and down. So there's no motion along the y-axis. So AY is 0. So that you have it to be 0. So all the forces acting there will be 0. And two forces acting there are R pointing in the negative direction and M2G pointing in the positive direction. So you have it to be minus R, because it's pointing in the negative y direction, plus M2G is equal to 0. That means that, therefore, R is equal to M2G. Let's call it equation 2 if you like. For mass 1, which is this one, I will go to redraw it beside here. For mass 1, remember we have something like this. M1, M1G, then T. For mass 1, along the y-axis, because there's no motion along the x-axis, so along the y-axis. So this is our y-axis. So along the y-axis, we have that sigma Fy, because there is motion now for that very particular mass. There's motion along the y-axis. So, and the motion is to now be, this is minus T, this place downward is plus. So we have minus T plus M1G is equal to M1AY. That is what we have, because this one is pointing up, is minus. So, but we find out that this rope is just a single rope connected. So if this one moves fast, this one will move fast. If it moves slow, this one will move slow, because the rope is inextensible. It is connecting the same. That means that but AY is equal to AX. That means if mass 1 accelerates faster, then mass 2 will accelerate faster. If it goes small, then this one will go slow too. So which means our ax is equal to ay. So if we do that, we find out now that from here, this implies that ay, which is equal to ax, is equal to m1g minus t all over m1. That's what we'll have. So let us now substitute, call it equation 3, and substitute it in the first equation that we got, and substitute it in the equation we got. It will now help us to find the fx. So if we do that, we get fs is equal to t minus, remember this is m2, t minus m2 into our ax is m1g minus t over m1. That's what we will get. So of course, we from our problem we see that m1 is 3 and m2 is 3, which means they are equal. That means m1 can cancel m2 because they are equal. m1 is equal to m3. m1 is equal to m2, so they can cancel. Now what we will now do is to substitute t. We have found that we were given that t is equal to 0.71 g. That's it here. So equal to 0.71 g. So we substitute in the equation and we'll get minus m1g minus 0.717 m1g. So this is 0.71 m1g, this is 1 m1g. 1 minus 0.7 will give us 0.3. So we'll have is equal to 0.7 m1g minus this one, like we said, is 0.3 m1g. So you now find out that 0.7 minus this will give us 0.4 m1g. After which now we'll substitute so that our fs will give us 0.4 times m1 we say is equal to m2 is 3 times g. Let's just take it to be 10 meters per second. So our answer will be in Newton. So that we see that 330, okay, 4 times 3, 12 Newton. So the frictional force is 12 Newton. So that is how to do this type of thing using free body diagram.